All right, so in the beginning of your Calculus 2, you learn that this integral is part of the basic rules of integration and that you're kind of asked to memorize it. But now at this stage, you're able to understand exactly where this arctan came from. And it always did involve a trig substitution, which involves triangle. And that's where it all came from. So in this session, you're actually going to understand where that odd formula came from, because it's quite unusual that this integral, after you take this, it would be arctangent x. So here you're going to understand exactly how this is solved. So the real reason why you need a triangle here is because this integral is very difficult to solve in terms of dx, which right now you have a dx integral. So this is so difficult that it is easier to translate it in the language of trigonometry. This is something that you're going to do full-blown towards the end of Calculus 2, when you actually can't take integrals unless you shift to polar coordinates or spherical coordinates. This is something you do in physics as well, and engineering classes, like the real sciences use this a lot. The integrals that are difficult to solve in terms of x, you translate it in polar coordinate system. This is rectangular coordinate system, right? So you translate it and then you solve it there, because it's much easier to solve it there. So we're going to do something similar here. This is kind of a softer version of what's coming later. So this is good to get used to it. Practical reason why we do it is because it's hard to take this integral without this. So now I need to spot that there is a triangle that I can assign this to, because there's Pythagorean theorem, because I have a square plus x squared sitting there. And what is the hypotenuse? One of the things that you need to get used to spotting right away is, where is the hypotenuse sitting here? And this has to be the hypotenuse, because there's no other side in the right triangle that where you square other two sides and then you add. That is only hypotenuse. This is formula for hypotenuse. So I'm going to write it here. And the vertical side wants to vary with respect to theta, so this likes to be x or x squared. Remember, in a previous video I said that I don't like to label the sides of the triangle where some of them are squared and some of them are not. Either all sides of this triangle will be squared or none of them will be. I usually like to go with none of them are squared, right? So now at this point, you are trying to move away from x's. Anywhere you have expression for x, you need to move away from that, because you want to solve a d theta integral. So you need to come up with an expression for this. So basically your task list is what is this equal to in terms of theta? And also, what does dx equals to in terms of theta, so that I can rewrite this integral in terms of some trig functions and d theta. So I'm going to determine that with, first of all, for me to get dx, I know I need x first, because dx is simply derivative of x. So first, I need to get expression for x. Then I can get dx very simply. But how about this expression? So I'm going to write down the ratio, which that is part of. And remember that trig functions are nothing but different possible ratios. And there are only 6 possible ratios when you have 3 sides, right? So there are different ratios, and that's what we call trig functions. So I'm going to use one of the ratios that involves this side here and a number. I don't want to connect this to x, because I'm trying to move away from x. So if I bring this in, then I have to isolate x. And if I have a way to connect it to simply a number, I would do that. And that ratio is cosine, right? And that's the one that we are very much familiar with. I could have chosen secant, because that way, if you can look here, if you only want to remember these more common ones, that's fine. But also understand that hypotenuse over adjacent is secant. So that I'm trying to isolate hypotenuse, so that way I would have this at the top. So I could have gone with secant, so that's fine. And secant theta always equals to hypotenuse over adjacent, but in this case, it equals to the square root over a. So now you can simply square both sides. So you get expression for this exactly. So this is secant square theta on the left side and over a square. And now I can bring this a square here so that I have isolated a square plus x squared. So I have expression for that. So I can rewrite this integral and say that this is simply a square secant square theta. Okay, now I need expression for dx. First I need to get x. So here I'm looking, I want x connected to a. I don't want to connect it to an expression that also in itself includes x. So I will go with tangent theta. That is opposite side to theta over adjacent, right? So that's going to give me equals to x over a, opposite over adjacent. So then x is a tangent theta, and dx is derivative of tangent theta. And derivative of tangent theta is secant square theta, d theta. Okay, so now I have expression for dx as well in terms of d theta. So I just copy it here, and then I can solve this interval. Notice that, get rid of this here. Notice that this interval is same as this interval, but it's now written in the language of trigonometry, and now I have d theta integral. And the reason why you do this, like a practical reason why you do this, is that usually a lot of things gets canceled after you do this, and it's such easy integral to take. So all I have left here is 1 over a, which comes out of the integral because a is simply a constant. 1 over a is also a constant. And I have integral of d theta. This is a very basic integral to take. This is no different than integral dx. A lot of the times people are, and I myself am smarter when x is the variable rather than any other letter. But rules are the same, right? So it's just theta plus constant of integration. By the way, if you notice, this is where the 1 over a comes in the formula for this integral in your basic rules of integration. The last step left to do is to now do the reverse, get rid of theta and express everything in terms of x, because we were asked a question in terms of x, even though we chose to solve it using thetas. The final answer needs to be expressed in terms of x, and that's easy enough because as soon as I have any trig function expressed, then here I have secant, I have all of these, so I can just choose, I can isolate theta from here, right? So I can say tangent, here I have that. So if I want theta, I can just say that theta equals to arctan x over a, correct? So now my answer is in terms of x, and that's the final answer. And now you know where the formula that you have already been using actually comes from. It involved trig substitution, so this is why it wasn't taught to you in the beginning, but now you get to know where this came from, and I think that's very satisfying because it's so frustrating when you're asked to remember something as an advanced mathematics student.